So let's look a little bit deeper into how this all works out and how we truly get to this infrastructure as code idea. So first off, we use our containers. We talked about containers earlier. Here I'm just showing two containers. We have a program with our version 1.1 of our application in it, and it's co-resident with a database. Well, since these need to be co-resident, what we're going to do is we're going to use Kubernetes, and we're going to put them into a pod, right? So now you see over here on the left, those two things are in a pod. So what we're going to do is we're going to apply that we want that pod to be run by taking our YAML file, applying it to the API server, right? At this point, the controller is going to say, hey, I need to schedule a pod, right? So it actually calls the scheduler. Now the schedulers will go out and look at each of the kubelets and say, hey, what's your CPU utilization, what's your storage, what's your memory, and keep all of that scheduled. So then the schedulers say, hey, put it on worker node 1 or worker node 2, whatever. So then the controller server says, okay, I'll change the type, you know, if you will, I'll apply it to the database. The database just is simply served up by the API server. So I'll change the database to say, put it on node 1. The next time kubelet checks into the API server, it says, hey, I want you to run this version 1.1 of our program and shoot up this copy of this container in this pod. So then the kubelet says, okay, gotcha, and it does it. Some of the other things that it'll do is the service discovery piece of it. It'll go ahead and do the dynamic DNS entry. So let's say we scheduled 3 versions of our program to run. We could put a front end service on there, and that would round robin them by using an ingress server. So it can do all of those things in the Kubernetes master node. Again, what a service is it's just a pseudo front-end node. It's actually another container which runs that just listens for calls, and then if you tell it to round robin or look for the least used or the last used, these types of things, the service will hand out the calls and load balance between versions of your program. It can also do things like the node port we looked at before. It'll allow you to do that. It'll allow you to map services, and it'll actually do a DNS server. We didn't look at that, but I can just use the name of my application and do an automated DNS entry, and then from the web I could just call it from its DNS name as well. So it'll do all that for you there. We talked about it does storage as well. It maintains storage. So here you can see a lot of different Kubernetes drivers. It does 2 different types of storage. It does one we call ephemeral storage. So within the pod itself, it can store variables and things on the local disk. The problem with ephemeral storage is once the pod is destroyed, the ephemeral storage is destroyed as well. Or if it fails, the ephemeral storage is destroyed. So you only use that to keep state for local things within the pod, but it's not something that's going to stick around. But you can simply declare a type of storage, and it can be anything. It can be Azure, it can be AWS, Elastic Block Store. Ceph is a big one for the open source community. GlusterFS is something by Red Hat. You can do any iSCSI, NFS, mount. Scale.io is down there. Pure has block, NFS, Flex storage available. So, and vSphere volumes can also be used. So there's any number of storages that you can apply and attach to your pods as well. The way they do that is you create what's called a persistent volume on the system, and that's an API that details how storage is available and provided. And that's really just a namespace, right? So there you're declaring my persistent volume can be, say, 20 terabytes of NFS, or it can be AWS, or however you want it. And then in your container, in your manifest, you type in a persistent volume claim type, And what that does is it requests some of that storage from the persistent volume, and Kubernetes hooks them together. So like I said before, the reason this is so powerful is the persistent volume may be out on a storage array. The claim is presented from the, say, the program version 1.1, but you may have 3 different versions of that, and they may need to read and write all to the same persistent volume. That's okay. The claim is that glue which glues it together, right? You can also have, you know, a master and a backup if your software works like that. One may be mounted read-write, and the other read-only to that same volume. So it gives you some of those kind of strengths by splitting this out into a 2-part namespace that then Kubernetes glues together as needed. Networking is also something provided there at the master node. We launch it as well. So on the pods themselves, you do have the Docker bridge. We use something called a 1 IP per pod model. So when you are reaching into the pod from the outside world, from the device itself, the worker node that it's running on, you're only going to get 1 IP address per pod. And the beauty of that is everything else talks simply as a local host. So as long as my program is running on one socket and my DB is running on another socket, it's just called from localhost. So I never have to know the IP address. And when I'm leaving, all my pod does is give it that port number on the pod's IP address. So now as the pod moves around, and again, the master node keeps track of where the service is and does all the load balancing and those types of things, it only has to keep track of the pod's IP address. So powerful model, again, a couple layers of obfuscation as to what the actual addressing is, but that means your programmers never have to care. They only have to call the port from localhost. This just shows you as well that they've created this CNI interface, right, container networking interface, and there are all these people have written CNI plugins. So you've got Amazon, Azure, Google Cloud, Juniper has, but Cisco has written an ACI plugin, right, as well as an OpFlex client plugin and Contiv networking. Those are all from Cisco. The Big Cloud Fabric from Big Switch Networks. NSXT has a container plugin, right? Their Pivotal platform as a service model has their PKS plugin, right? OpenShift does from Red Hat. Infoblox has, everybody's writing to this because now you can cross-connect between containers. The other beauty of this is you can run something in your network, like say you run a Big Cloud Fabric, that can reach out, it can talk to your Cisco gear, it can talk to your Arista gear, it can talk to your NSXT controller, it can also talk to Amazon, Azure, and you can actually start now to hook together on-prem and multiple clouds into a single Kubernetes workspace. And it's done by using this, again, this obfuscation layer of networking and how they've built that with the Container Network Interface plugin. Something else they're producing are something called service meshes, and we'll go into a little bit of this. And what this is again, it was written by Google and Lyft, the car service, created the proxy component, and IBM actually did some of the code to glue this together as well. But what this does is it starts to look at services, not from a layer 3-4, not from a container sort of point of view, but actually from the service the customer uses, right? That can contain multiple containers and multiple microservices out there. And it just is literally reaching around, load balancing these, that you could have one running on-prem and one running in Azure, and it can load balance both of those two services, right? So it does service discovery as a service, not from a container level as Kubernetes does. It injects something called a sidecar. The sidecar actually resides in the pod, and it proxies all the input and output that occurs within the pod, right? What can you do with this? Well, now you can do access control layers per service. You can actually encrypt the traffic between any two services, between pods, between machines, automatically. It sets up and it controls and it rotates the keys and all these things. So it provides actual service encryption that's been missing in a lot of these things that roll out. The other beauty of this, layer 7 telemetry, so you actually can start to watch your application from end to end. And there are several tools we'll look at, Grafana, Zipkin, FluentD, Prometheus, that ship with Istio and provide you the visibility at a service level. So not a machine level, but a service level. The other thing it allows you to do is, since you can set these ACLs per individual service, I can now load balance between different versions of the service in the same container, right? And let's say my service gets too much latency latency in it, I can back out, or I can shut down that endpoint and push my traffic elsewhere. So it gives you fine-grained control at a service level of actually how you have your traffic move. So what does that look like? Well, we have an Istio controller node. It consists of 3 parts, what we call pilot, citadel, and mixers. And then we inject this sidecar into the worker node. The sidecar grabs all the external traffic, right? It exits its telemetry data out to the mixers. It gets its keys and sets up its encryption from Citadel. And Pilot actually sets up the ACLs, understands the services, goes out and sets the proper connectivity between the various services. So this provides you with whitelist security, east-west security within a worker node, encrypted traffic even within a worker node, and fine-grained telemetry output, which we can then take out of the mixers and send to these different service visualizations. So what would some of that look like? Well, let's do a demo of some of the tools that ship with Istio and run on top of the Kubernetes and help you look at your traffic and understand your traffic from a service level. So here we go. Let's demo some of these tools. On this site, I want to generate some load. And the reason I'm doing this is I'm going to keep reaching out to that page every few, or 0.2 of a second. And I'm going to try to pull enough information to actually look at what's going on here. So each one of these dots is a request. So the first thing I'm going to do is I'm going to go over to the included Grafana dashboard. Now what Grafana is a included website that's somewhat of a tool to actually go in and look at the operations per second, the success rate, the load, these types of things. So here I can see my cluster. I can see my version 3 of my reviews. The success rate is 100%. I actually, since I modified the rules, I'm not calling version 1 or 2, so you don't see any there, and you can see the product page and the ratings. I'm also putting out telemetry, I'm checking my policy, and I'm doing my details there. So for any one of these, I can actually go into the cluster, and I can see how that cluster is working. So I can see what my operations per second are, what my success rate is. I can come down here and look at my traffic and go through here and see the various things as a service. Again, we're not necessarily looking at it as a container itself or anything like that, but I'm actually looking at the service here and what's going on in that service, right? You'll notice here some of the P50s, P90s, and P95. We're looking at different percentiles here. That's what the 3 different colored lines are. And they show us actually what's going on. So some of the other things, besides just looking at the individual service, I can go and look at snapshots. I can play and stop the service. I can set up alerting rules as well. So those are some of the things that you do with the dashboard here. I'll just go back to the home dashboard here and see what's going on. I could add users to do role-based access, those types of things. And then I'll go back actually to look at my service dashboard. and I can see what's going on there. So it's just a tool that allows you to take a look at, what's going on with your systems and look at it actually by service.